Welcome to the Tech Study channel. In the previous class, we have discussed about uh, seventh important question and its answer of Triple E subject. Now, in this class, I will explain eighth important question and its answer. So, in this video, we will see only half uh, answer of this question transistor because the eighth question is transistor act as a switch and amplifier with diagram. So we have to explain this. So uh, transistor is of two types. One is current controlled transistors are there and voltage controlled transistors are there. So for the example for controlled transistor is BJT, and for voltage controlled transistor is FET. So means field effect transistor. So for BJT we will discuss in this video, and for FET we will discuss in the next class. So first we will see what is transistor. So first we will see what is transistor, then BJT, then EBC definitions, means emitter base collector definitions, and doping and its types and voltages of transistor. Then we will see CB connection of BJT, means bipolar junction transistor, and definitions of IC, IB and IE, and three regions of BJT, means active region, saturation region and cutoff region. In the CB connection only, common base connection. So first, what is transistor? Transistor, a fundamental semiconductor device used to switch or amplify electronic signal and power. Switching means switching on or off, and amplifying means increasing the strength of the signal. Then this is the tiny transistor which have three terminals: emitter, base and collector. And then transistors are categorized by whether they are controlled by input current or input voltage. If they are controlled by input current, they are called current control devices. Example BJT, bipolar junction transistor. And if they are controlled by input voltage, then they are called voltage control devices. Example FET, field effect transistor. So what is BJT? BJT is a device where a small current at one terminal controls a much larger current flowing through the other two terminals. Okay, then these are the two types of transistor, not BJTs. So I have said in the last video, I have said it wrong, so rectify it. So there are two types of transistor. One is PNP transistor and NPN transistor. So in NPN transistor, as we know, two N terminals, which are collector and emitter, and one P terminal which is base. And PNP transistor, which has two P type materials, which is collector and emitter, and which are collector and emitter, and one is n-type material which is base. And in the circuit they are represented like this. And then arrow mark, this arrow mark indicates, emitter arrow mark indicates the flow of the current. So emitter supplies charge carriers, electrons or holes into the base. So here is the emitter terminal is there, which supplies charge carriers, which means electrons or holes into the base. Okay, and it is heavily doped, and base controls the flow of charges from the emitter to the collector, from the emitter through the base to the collector. Okay, and it acts like a gate for the transistor, and it is lightly doped, and collector collects the charge carriers provided by the emitter. Collector, it collects the charge carriers provided by the emitter through base only. Okay, then it is moderately doped. So why they are heavily, lightly and moderately doped means, so to understand it we have to understand what is doping. Doping is a process where a tiny amount of impurities are added to pure semiconductor crystal like silicon or germanium to make better at carrying electricity, because the pure semiconductor are poor conductors at room temperature. So then doping is useful to introduce either extra electrons or holes to serve as charge carriers in the pure lattice or crystal like silicon or germanium. So it introduces extra electrons in the n-type material and extra holes in the p-type material. And then, so why they are lightly, heavily and moderately doped means, heavily, lightly and moderately doped means emitter is heavily doped to supply maximum charge carriers. Here emitter in the NPN transistor, emitter is of n-type, so it is heavily doped means the more number of, or the more amount of extra electrons added to this emitter. So what's the function of emitter? It supplies charge carriers. So it is heavily doped means it contains more extra electrons, so it can supply more charge carriers or maximum charge carriers to the base. Okay, charge carrier means holes or electrons or holes. And then the base is lightly doped and thin to minimize recombination of carriers. So in a NPN transistor, base is of n-type. So it is lightly doped and thin. Means lightly doped means less amount of extra holes are added to the base. So Why it is lightly doped means if it is heavily doped means more number of holes are added or introduced to the base through doping, then the holes of base will be combined with electrons of the emitter, with the electrons which is supplied by the emitter. Okay, so there is no current flow in the base to collector, because more number of electrons which is supplied by the emitter are recombined with the base, so there is less or no current flow from the base to the emitter, collector to the emitter, okay, collector to the base. Okay, or we can say that there is no or less current flow between base and collector junction. Okay, then collector is moderately doped to handle high voltage or heat while collecting carriers. Here is the collector, it is moderately doped, so its function is to attract the electrons from the base terminal. So if it is heavily doped, then the heat or voltage will be more, so to avoid that it is moderately doped. Then we will see types of doping. N-type doping and P-type doping is there. So example is pentavalent elements which has 5 valence electrons. Example phosphorus and arsenic are added to a tetravalent which has 4 valence electrons. Example silicon lattice. The fifth electron cannot participate in the covalent bonding, becoming a free electron available for conduction. So the material is with an excess of negative charge carriers, electrons. And then p-type doping example. So in this n-type doping example, we have seen the process of doping a n-type material. Okay, next p-type doping means tetravalent element which has 3 valence electrons. Example boron, aluminum are added to a tetravalent element which has 4 valence electrons. Example silicon lattice. The impurity only has 3 electrons to bond with 4 neighboring silicon atoms, leaving a missing electron site known as a hole. So the material is with an axis of positive charge carriers, holes. So in this way we are doping a p-type material. Then we will see the voltages of the transistor, VC, VB and VBC. So are the voltages between terminals that determines the operating region, cutoff, active or saturation region. So what is VC? Voltage between the collector and emitter, and it creates a strong electric field at the collector to attract the base electrons or charge carriers. Then VB, voltage between base and emitter. It is responsible for flow of electrons from emitter to base. It must be 0.7 volt for silicon active or saturation region. Okay. Then VBC, voltage between base and collector, VBC. It is responsible for flow of electrons from base to collector. Okay, then we will see what is CB connection. CB connection means so CB connection is like this only. So where the input is taken between emitter and base, and which is here, input is here, and output is taken out from the collector and base. Okay, here the base terminal is common for both input and output circuit, so the name is as common base connection. Okay, then what is IC, IB and IE means? They are collector current, base current and emitter current. Here, collector current means the electrons that successfully survived the drip across the base and entered the collector. Means the electrons that successfully survived the drip across the base and entered the collector is called collector current, which is responsible for collector current. So, through diagram, here it says the electrons that successfully survived the drip across the base and to the collector. We already know electrons flows from emitter then to base and then to collector. So base contains holes, so which does not get recombined with the holes of the base and successfully survive the drip across the base and enter the collector. Okay, that is IC current. And then IE current, the total budget of electrons sent into the transistor. The total budget of the electrons that are sent into the transistor. Okay, then IB current, the small loss of charge carriers that fail to reach the collector and instead exit through the base terminal. Here the small loss of charge carriers at the base terminal, okay, that fail to reach the collector. So here electrons are moving from emitter to base to collector. Then the IB current, base current, is the small loss of the electrons that fail to reach the collector, means which are recombined with the holes of the base. Okay, which are recombined with the holes of base also, and this is the one condition or reason of electrons by which they are exit through the base terminal. So there are three reasons. One is, so as we know, when electrons enter the p-type base from the emitter, they are minority carriers. Huh? And since the base has many holes, a few electrons fall into these holes and disappear, means recombination occurs. This is the first reason. And the base terminal is connected to the positive terminal of the battery. Here is base terminal is, so I have shown the diagram of cutoff region. So here is base is connected to positive terminal. So this positive terminal acts like a vacuum cleaner for electrons. And then third reason is, when an electron in the base recombines with a hole, the base loses a hole and becomes slightly more negative. To fix this and keep the base working, the battery pulls an electron out of the base terminal or pushes a hole in the emitter. Here, when an electron in the base recombines with a hole in the base becomes slightly negative. So to fix this, the battery pulls out an electron or pushes a hole into the emitter. Okay, to maintain the charge neutrality. So what is charge neutrality means? It is the state where a material or region has an equal number of positive and negative charges, resulting in a total net charge of 0. So uh, to prevent from becoming negative, the base negative, to prevent the base from being negative, this positive terminal or battery is maintaining charge neutrality. Okay, then we will see three regions of common base connection, BJT. So as the question is, transistor act as a switch or amplifier. So a transistor act as a switch by operating in its cutoff or off switch or saturation, means on switch regions, to control high power loads with lower power signals, and as an amplifier by operating in its active or linear region where a small base current produces a proportionally larger amplified collector current. So this means in the cutoff region it acts as a off switch, and in the saturation region it acts as a on switch, and in active region it acts as a amplifier. Okay, then we will see one after the other regions. First cutoff region, then active, then saturation region. Then cutoff region means both junctions are reverse biased, EB and CB junctions. Here both junctions are reverse biased because p-type terminal is connected to negative, P-type material is connected to negative terminal and N-type material is connected to positive terminal. And here P-type material is connected to negative and N-type material is connected to positive terminal. So that's why they are reverse biased. So the transistor is off, and in this region this VEE and VCC voltages means supplied voltages. These are supplied voltages, VEE and VCC. VEE is 0 and VCC is equals to positive high. And VEB transistor voltages are VEB is low positive and VCB is high positive and VCE is high positive. And IC, IB and IE is equals to 0. So we will understand this by using an example. So in this I have taken VEE is equals to 0 and VCC is equals to 0, which satisfies this conditions. VEE is equals to 0 and VCC is positive high. And then the transistor voltages are VEB is equals to 0, which is low positive, and VCB is 10 volts, which is high positive, and VCB also high positive. VCB and VCE are high positives, 10 volts and 10 volts. Then we are measuring IB, IE and IC. Okay. So we got 0, 0 and 0 only currents also. So how we got means by applying KVL at input circuit and at output circuit. If you apply KVL at input circuit here, then what it will be? So we got here I will explain what are the voltages, means sum of the voltages will be 0 now. Then VEE minus VEE voltage is there and VEB also there minus VEB, because VEB is negative because E is of N type and base is of P type. So we are measuring current at emitter compared to base. So we have to take negative here. Okay. Then another one is IE into RE, that is equals to 0. So we need IE from this equation. So IE is equals to VEE minus VEE plus VEB by RE we get. And if for getting IC equation, we are applying KVL at output side. So we get a VCC minus this voltage minus VCB, okay, VCB. Here we are taking positive only VCB because C is a negative terminal. Means N type terminal and base is a positive terminal. And then IC into RC. IC into RC, that is equals to 0. We need IC, that will be VCC minus VCB by RC. Then we are calculating for these values. Now here I have calculated here. VE is, we have taken 0, and VEB, where it is, VEB 0, and VEE also 0. Then 0 plus 0 by 1. RE, we have taken 1 kilo ohm. Okay, then that is equals to 0, and IC is equals to VCC minus VCB by RC. Means VCC and VCB values are, VCC is 10 and VCB also 10, and by RC value is 1. So 10 minus 10 by 1, that is equals to 0. And then IB, through transistor equation I have calculated, that is IE minus IC. 0 minus 0, that is also 0. So we have calculated the emitter, base and collector currents. And then in active region, the EB junction is forward biased. E and B junctions are forward biased, and CB junction is reverse biased. Means N-type material is connected to negative and P-type material is connected to positive, means forward bias, and P-type material is connected to negative and N-type material is connected to positive terminal, so it is reverse biased. So then the transistor acts as an amplifier with IC almost equal to IE. Okay, means it increases the strength of the signal, which is here input signal. It increases its strength. Then here the VEE value is negative medium. Okay, and VCC is high positive, and VEB is negative between minus 0.7 to minus 0.8 volts, and VC is medium to high positive, and VCB is medium or high positive. So and IB is very low and IC is medium. So in the cutoff region, we got the current values 0 only. After measuring also we got 0, 0 and 0. Okay, and coming to active region, so in the example, here is the example, we have taken VEE, that is equals to minus 2 volts. VEE is negative medium, so we have taken minus 2 volts, and VCC is positive 10 volts, which is high positive, that's why we are taken 10 volts. Then we got the VEB and VCB and VC values are minus 0.7 volts, which satisfies this condition, negative between minus 0.7 to minus 0.8 volts. And VCB we got 8.73, medium or high positive, it is also like that only, and VC is equals to 9.43. So VC is medium to high, positive. And then we have to measure IE and IB, IC. So IE we have derived the formula from KVL. So VE plus VEB by RE. So here VE is minus 2 and VEB is 0.7. So where is VEB? VEB is minus 0.7 here. So why we have taken here positive means already in the calculation we have taken VEB as negative only. So that's why we are making this negative value to positive value. Then we get the minus 1.3 microamperes. So we always measure the current in terms of positive values. Then we got 1.3 microamperes. Then IC is equals to VCC minus VCB by RC, that is equals to VCC is 10 volts and minus VCB is 8.73 by RC. RC is 1 kilo ohm by 1, that is equals to 1.27 we got. So we can measure it by alpha also. If we know alpha then only. Here the alpha is 0.98. So 0.98 into 1.3, which is already emitter current, that is equals to 1.27. And then IB we are calculating from transistor equation, IE minus IC, 1.3 minus 1.27, that is equals to 0.03 microamperes. So we have to check now, is this IB, IC and IE values are satisfying these conditions or not. So IB is very low. So IB is 0.03. Yes, we got very low values as compared to these two values, IC and IE. And these are medium values. Medium only, 1.3 and 1.27. Okay, then saturation region. Both junctions EB and CB are forward biased. Here so VEE and VCC are forward biased, means positive to positive, P-type to positive terminal and N-type to negative terminal, P-type to positive terminal and N-type to negative terminal. Then the transistor is fully on, switch acting as a closed switch. And here VE is high negative and VCC is low positive. And VEB is high negative and VCB is less than 0.3 volts and VC is very low positive. So IE, IC and IB are high. So we have taken example. So what's the condition for VEE and VCC? It should be high negative and it should be low positive. These values are satisfying that. Then we got the VEB and VCB and VCE values, minus 0.7, 0.2 and 0.9. And then we are measuring IC, IE and IB. So VEE plus VEB by RE, that is equals to 1.7 VEE here. So here minus 1.7 is there, then plus VEB minus 0.7 volts. So as I've already said, we have taken negative VEB in the calculation of a formula only. So we are not taking here negative. So we are taken we have taken positive 0.7. So we get minus 1 by 1 minus 1 by 100, that is equals to minus 0.01. And if we multiply this, we get into 1000. To convert into microamperes, we are multiplying it with 1000. So we get minus 10. That will, so we always measure current in positive values only. Then we considering 10 positive 10 microamperes. Then IC is equals to VCC minus VCB by RC. VCC is 1 volt and VCB is 0.2 volts by RC we have taken 100 ohms, that is equals to 8 microamperes, that is equals here, that is equals to 8 microamperes. Then IB is equals to IE minus IC is equals to 10 minus 8, that is equals to 2 microamperes. Then we are verifying these values are satisfying the conditions or not. So VB is high negative. So minus 0.7. Here the VEB is high negative, means minus 0.7, and VCB is 0.2, means it is less than 0.3 volts, and then VC is 0.9 volts, very low positive value. Voltages are satisfying. Then we will check currents. These three currents should be high. So IE is we got 10 and IC we got 8. It is also maximum. These two are maximums. And IB we got 2 microamperes. So this is lesser than these two currents, because then only the more number of electrons will flow from emitter to collector. Okay, then so in the cutoff region, why the current does not flow means VE is low, the input voltage is supply voltage is low, it is kept below 0.7 volts. Since means in the example we have taken 0, since it can't overcome the barrier of the emitter base junction, no electrons are pushed into the base. Okay, then VCC is high, it sits ready to collect electrons, but since the emitter isn't sending any, so no current flows. Okay, and in active region, why is signal amplified means VE is medium, it is high enough usually greater than 1 volt. In the example we have taken, VE is minus 2 point, so it is negative medium here, it is negative median value, so it should be minus 1. less than, or we can say medium negative value to overcome the 0.7 volt barrier and push a controlled amount of current, IE. So VCC is high. It provides a strong positive pull to sweep almost all these electrons from the base into the collector. So here we have taken 10 volts in example. And then in saturation region, why current becomes constant? Means VE is high. It is pushed high to flood the transistor with as many electrons as possible. Okay. And VCC is low because the supply is low and the current is very high. The voltage drop across the collector resistor RC is so large that the collector resistor RC, I have written here the repeatedly, the voltage drop across the collector resistance RL is so large that the collector resistance, here it is, the voltage drop across the collector resistance RC is, it is not repeated here because the supply is low and the current is very high. The voltage drop across the collector resistor RC is so large that the collector resistor RC is so large that the collector voltage drops near or below the base voltage. This causes the gate at the collector to open up, making it forward bias, and the current becomes constant. Okay. And then that's it for today's class. If you feel this video is helpful, then subscribe, like, share, and comment. I will see you in the next class. Thank you. Bye.